Hi there. In today's lecture, we're going to be looking at complex numbers. So before we start, just quickly, what are complex numbers? So we'll see that complex numbers is a number system that extends the real numbers. So we write the real numbers, and then it extends to the complex numbers. So the complex numbers contain the real numbers and more numbers as well. Okay, so it's a separate number system, much like how the natural numbers is contained within the integers. So the integers contain positive numbers, negative numbers, and zero, and then the natural numbers are only the positive numbers. Okay, so we'll see how these complex numbers extend what we know from the real numbers. Okay, so where do these complex numbers come from? Okay, so the complex numbers come from the problem of finding the roots of a polynomial. Okay, so that's where they were first invented or discovered. So given a quadratic polynomial, okay, so let's say ax squared plus bx plus c, we can attempt to find the roots of this polynomial. Okay, of this polynomial. Okay, so I say attempt because we might not always be able to find the roots. So if you remember back to your high school days, when you looked at the roots of a quadratic polynomial, you could use the quadratic formula, and sometimes you get a single root, sometimes you get two different roots, and sometimes you get no roots, or you might have written no real roots. So we're going to see here, to solve that problem of having no real roots, we extend the real numbers into these complex numbers, which we'll look at, and that allows us to find all the roots, okay, whether they're real or not. Okay, so for now, we just say attempt and see what we can do. So for example, let's say we had x squared plus 2x minus 3. We set that equal to 0 to find the roots. In this case, we can factor this quite easily. So this will be x plus 3, x minus 1. You can check that quickly just by multiplying this out. So here we get x plus 3 is equal to 0, so x equals minus 3. And on the other side, x minus 1 is equal to 0, x is equal to 1. So here we have two real roots for this quadratic polynomial. Okay, so everything's fine with that. So we can use factoring, or we can use the quadratic formula. So we can write x is equal to minus b plus minus the square root, b squared minus 4ac all over 2a, and we can simplify this. So this is going to be x equals minus 2 plus or minus root 16 all over 2. We can further simplify this, so that's going to be x is equal to minus 2 plus or minus root 16, that's going to be 4 over 2. And finally, dividing by 2, we get minus 1 plus or minus 2. And depending on if we take the plus or the minus, we get our two solutions. So let's take the plus. So minus 1 plus 2, that will be 1. If we take the minus, we get minus 1 minus 2, that will be minus 3. Okay, and those are the same roots that we had before, minus 3 and 1. So we can either factor, or we can find the roots using the quadratic formula. And in this case, we got the two real roots. Two real roots. Now, this might not always happen. Okay, so here we got two real roots for this quadratic, but in general this won't happen. So for example, if we have x squared plus 1 is equal to 0, you can try and factor this, you can try and use the quadratic formula, you won't get a solution. Okay, so here we can't factor it, there's no difference of squares that we can use, so that doesn't work. If you were to try use the quadratic formula, you would end up with a negative under the root sign, and that doesn't work. So here, this does not give 2 roots. Okay, in fact, it does not give any roots. Okay, so you can either try those other two methods, or we could just graph this quickly. We see x squared plus 1 looks like this, something like that, and we see there's no intersection with the x-axis. So no x-intercepts, no roots. Okay, so that's another way of checking. We see that it's above the x-axis here, so no solutions to that equation. X squared plus 1 is equal to 0. However, we would like there to be 2 solutions, because there's this theorem called the fundamental theorem of algebra. Fundamental theorem of algebra. Okay, and this theorem states that a polynomial of degree n will have n roots. So a polynomial of degree n will have n roots. So we see that this sometimes applies to quadratic, like we had in this first case over here. We had a quadratic degree 2 polynomial and we got 2 roots. But here we have also a degree 2 polynomial, but this has no roots. So we would like to force it to have n roots if it is degree n. Now, like we had here, there's no real solution for that. However, there's always an extended solution or a complex solution. So the way that we do that is we define this new number we call I, and this is defined to be square root of minus 1. Now we know from working with real numbers that this doesn't give a real number back. So if you have the square roots of minus 1, that doesn't make any sense in terms of real numbers. However, this number is not real. We say it's complex. Okay, so we define I is equal to root minus 1 as a new unit, like 1 or minus 1, a new unit, for our extended number system. So we take the real numbers and then add this as well, as a new addition to it. Okay, so note, I is not a real number. Right? Because again, we can't take square root minus 1. That doesn't make sense in terms of real numbers. Instead, I is called an imaginary number. Imaginary, or in general, complex. Okay, so it's just a number for our new number system. Okay, so together with the real numbers and this new number I, new imaginary number I, we form the complex numbers. So the complex numbers is the real numbers plus some extra bits, so plus more terms. Okay, so what we mean by this is that the real numbers are contained in the complex numbers, but there's more stuff added on to get from the real numbers to the complex numbers. Okay, so why is this imaginary complex number I important? So why it is important or useful. Okay, so it's important or useful because this new number that we invented, this root minus 1 number, is the solution to that equation that we couldn't solve. So remember that equation, x squared plus 1 is equal to 0. This new number I is in fact a solution to this. So we couldn't find real solutions, but we can find complex solutions. Okay, so I, this new number, is a solution, and minus I is also a solution. And here, now that we're working with these complex numbers, we see that this quadratic indeed has two solutions, like we wanted. Okay, so by including these imaginary numbers, the numbers with the R, we then get what we want, and that is all these quadratics will now have two solutions. And if you have a cubic, you're guaranteed to have three solutions, or a fifth order polynomial that will have 5 solutions. Now, it may not always be real, okay, like we have here, but you are guaranteed complex solutions. Okay, so here we could factor this using these complex numbers now. So we could write this as x plus r, which is the one solution, x minus r, that's the other solution. So we can factor it using the roots. And just to check that this works, let's multiply this out. So x times x, that will be x squared. X times minus r, that's minus ix. R times x, that's plus ix. And then minus r times r, we can write that as minus r squared. But remember how I is defined? I is equal to the root of minus 1. So r squared, that will just be minus 1. That's the defining feature of this imaginary number, I. When you square it, you get a negative number. Now that doesn't happen in the real numbers. If you square any real number, you end up with something positive. But if you square a complex number, in this case if you square I, we get minus 1. And we'll see later on, if you square a complex number, you get back a complex number. Okay. Now the nice thing with this, the minus ix and the plus ix, they cancel, and the r squared, that's going to be minus 1. So we have minus 1, and that'll be plus 1. Okay, which is what we wanted to show. So indeed, this plus I and minus I are the roots of this polynomial. So x squared plus 1 equals 0. Has two imaginary, okay, that's what we call this I, it's an imaginary number, or in general we call it a complex number. Okay, we'll get to that now. Complex roots. Okay, so I and minus I, and we'll get to more examples, are examples of complex numbers. So those are a couple examples there. So in general, we can write okay, so for some randomly chosen complex number, we usually write it as z. Okay, so you'll see in textbooks and online and so on that we commonly use z to represent a complex number. So z is equal to a plus I, that imaginary number that we created there, times b. This a part of the complex number we call the real part. Okay, So that's just the name that we give to this part. So the part without the I we call the real part, and the part with the I we call the imaginary part. Okay, so any complex number can be written as the sum of the two parts. We have the real part A and then the imaginary part B, which is always attached to our imaginary number I. Okay, so that's how you can remember. So the I for imaginary, anything attached to that we call the imaginary part. So A and B, those are real numbers, and then together like this, we say Z is a complex number. And we write that with this fancy looking C. So like the R with the double slash here for the real numbers, the C with the slash here for the complex numbers. Okay, so C for complex. Okay, and since we have these two parts to the number, these complex numbers actually form a two-dimensional number system. Okay, so we'll see what I mean now. So these complex numbers, Z, form a two-dimensional number system. Okay, so two-dimensional because there are two parts to the number. So for real numbers, it's one-dimensional. You only have the number. With complex numbers, it's two-dimensional because you've got two parts to them. You've got the A, which is the real part, and the B, which is the imaginary part. We can also extend this to other number systems. Okay, so we won't go into this much further, but there are other number systems, let's say W, which has A plus R times B plus J times C plus K times D. These are called quaternions, and they are a further extension of the real numbers. So the A plus RB, that was the complex part. We can also add J times C and K plus D, and we end up with something called the quaternion. So we can extend this to further dimensions, and we see this will be a four-dimensional number system because we've got the A, B, C, and D. Okay, but this is just a side note. We won't go into that any further. Okay, so two-dimensional complex number system because any complex number can be written in terms of its two parts. And a good way of displaying these complex numbers is using what's called the complex plane or the Argand plane, where we have the real part along the horizontal, we have the imaginary part along the vertical, and any point here that represents a complex number. So this horizontal part A and this vertical part B, so that's just the distance there. We can write this as Z is equal to A plus IB. So here we have IB. Okay. So this works for any complex number. So just as a little example here. So here we have the real part. Here we have the imaginary part. We've got 0 in the middle. 1, 2, 3, 4. Minus 1, minus 2, minus 3, minus 4. Okay, so that is the real number line. And then remember, we added this new number I, and that extends it into this other dimension, okay, with the imaginary axis. So here we have I, 2I, and so on going up. And then we have minus R, minus 2R, and so on going down. Okay, so a couple examples. This point here, this will be 2 plus I. The real part is 2, so that goes along the horizontal part. The imaginary part is 1, because it's 1 times I, and that will be the vertical part. This point over here, we will write as minus 3 plus 2I. So minus 3 along the real line, and then plus 2 along this imaginary line, so we get plus 2i, okay, because we're going in that imaginary direction. Okay, another point here, this will be 2 minus I, so plus 2 in this real direction here, and then minus I because we're going down into this negative imaginary part. Okay, and you can plot several other points based on the real part, horizontal, and imaginary part, vertical. Okay, so just to summarize this, each point in this complex plane has a real part along the horizontal line okay, real part along the horizontal line, the real axis, and an imaginary part along the vertical line. Okay, or horizontal axis, vertical axis, however you want to think about that. So the real part goes along the horizontal, and the imaginary part, that goes along the vertical. Okay, so that's one way of representing these complex numbers. Okay, since they're two-dimensional, because you've got the real part and the imaginary part, we need a two-dimensional plane to represent them like this. Okay, now at the beginning, I said that these complex numbers are a number system, and as with any number system, we have operations between these numbers. So like with real numbers, we can add and subtract them, multiply and divide them. We can do the same thing with complex numbers. So, first thing, how do we add or subtract these complex numbers? So, addition and subtraction. Okay, so let's say we have two complex numbers, Z1, A1 plus I, B1, and Z2, A2 plus I, B2. So any complex number Z, remember we can represent them with a real part and an imaginary part like this. Okay, and that's true for any complex number. You can always separate it into its two parts. Okay, so firstly, how do we add them? So Z1 plus Z2, what do we do? Well, let's write down Z1, that's A1 plus I, B1, plus, and then Z2, A2 plus I, B2. Now, there's only one way that we can really add these two together, and that is, first we can drop the brackets, so A1 plus I, B1, plus A2 plus I, B2. Now, notice that the A1 and the A2, we can write that together, A1 plus A2, and the IB1 and the IB2, they both share a common factor of I. So we can factor that out, just like any number. We can factor it out, and we're left with B1 plus B2. And we see that if we ignore the inside parts of the brackets and just look at the brackets as a whole, we get that the first bracket is the real part of our new number, Z1 plus Z2. And the second bracket, again, just ignoring what's inside, we've got something in brackets plus I times something. That other part must then be the imaginary part. Okay, so if we look in the brackets now, we see that if we have Z1 plus Z2, then the real parts add together, plus R times, and then the imaginary parts add together. So, quite simple. If we add two complex numbers, the real parts will add, and the imaginary parts will add. Again, separately. Okay, let's look at an example. Let's say Z1 is 2 plus I, and Z2 is 3 minus 2I. So we want to find Z1 plus Z2. that's going to be 2 plus I for the first one, plus 3 minus 2r for the second. As we did before, we can drop the brackets, so 2 plus I plus 3 minus 2r. We can rearrange things, so we can have the 2 plus the 3 together. And if we factor out the I, we're going to have I brackets. There's going to be a 1 left over from the first term and a minus 2 left over from the second term. Okay, so here we've added the real parts together for the first bit, and we've added the imaginary parts together for the second bit. So 2 plus 3, that's going to be 5, plus I times 1 minus 2, that's minus 1. Okay, so you can leave it like this, or you can write it as 5 minus I. Okay, but if you want to keep it as the real part plus I times the imaginary part, that's fine as well. Okay, but this minus 1 times I, we can write that as minus I. That's perfectly fine. Okay, similarly, we can do the same sort of thing for subtraction. So Z1 is A1 plus IB1. Z2 is A2 plus IB2. We can now subtract the 2, Z1 minus Z2. Okay, so we have A1 plus IB1 minus A2 plus IB2. Now here we can't just drop the brackets because we've got a minus in front. So we need to be a bit careful. So A1 plus IB1 minus A2 minus IB2. Okay, so the minus needs to distribute inside. You can't just drop the brackets. Now, as with the previous case, the A1 and the A2 we can group together, plus I, and the B1 and the B2 we can group together. And notice we have a similar thing to what we had before, but now we have subtracted the real parts together, and we've subtracted the imaginary parts, again, grouping them together, okay, with the I in front. So again, we've got the real part, and we've got the imaginary part. Okay, but now instead of addition, we have subtraction between them because we have Z1 minus Z2. Okay, let's look at an example with some actual numbers. So Z1 minus 1 minus R, Z2, let's say, is 3 plus 2R. So we want to do Z1 minus Z2. Okay, so we'll follow the same steps as before. We can write this as minus 1 minus R minus 3 plus 2R. And again, the minus needs to distribute inside. So we have minus 1 minus R minus 3 minus 2R. The minus 1 and the minus 3, those make up the real part. So we can group those together. So minus 1 minus 3, that will be a minus 4. The minus I and the minus 2I, they make up the imaginary part. We can combine those into minus 3R. Okay, and again, we've taken two complex numbers, we've subtracted them, and we end up with another complex number. So the minus 4, that's the real part of the complex number. Minus 3, that's the imaginary part of the complex number. And together, it's another complex number. So given two complex numbers, we can add them together and get a complex number, or we can subtract them and again get a complex number. Okay, let's have a look at multiplication now. So that's the second bit. Okay, so addition and subtraction we group together because those are fairly similar operations. For multiplication and division, they're a bit more different, so we separate them out. Okay, so multiplication. So here we have Z1, A1 plus I, B1, and we have Z2, that's A2 plus I, B2. Now we want to find Z1 times Z2. So we can write this in brackets like we had before. a1 plus I b1 brackets a2 plus I b2. Okay, so how do we simplify this? Well, we just treat it as any numbers and distribute. So multiplying the a1, we get a1 a2 plus I a1 b2. Distributing the b1, remember the I, we have I b1 a2 plus r times I, that's going to be I squared, and then b1 b2. Okay, now remember r squared, the defining feature of I is that r squared is minus 1. So in the next line, we can replace r squared with minus 1. So we get a1 a2 plus I a1 b2, plus I b1 a2 minus, because of the r squared, b1 b2. Okay, and like we did with the multiplication, with the addition and subtraction, we can group together the real parts and we can group together the imaginary parts. So grouping together these real parts gives us a1 a2 minus b1 b2 plus I, and then the imaginary parts we can put together a1 b2 plus b1 a2. So it's a bit more complicated than what we had before. It's not like we just multiply the real parts together and the imaginary parts together because we have those cross terms. Okay, so when we multiply two terms here with another two terms there, we end up with 4 terms. So we can collect the real parts. Again, it looks a bit messy, but that's just collecting the real parts and then collecting the imaginary parts. Okay, so here again, these make up the real part, and this makes up the imaginary part. And since we have a real part plus r times an imaginary part, we get back a complex number. So the product of two complex numbers is again a complex number. Okay, let's have a look at an example with some actual numbers. So let's say z1 is 1 plus 2i, and z2 is 3 plus 2i. We want to multiply them. So z1 times z2, we can put these in brackets. 1 plus 2i, 3 plus 2i. And then we just distribute as we would with any other numbers. So 1 times 3, that's 3. 1 times 2i, that's 2i. 2r times 3, we can write that as 6r. And 2r times 2r, that's going to be 4r squared. And remember that r times I, or r squared, that's going to be minus 1. So we must remember that for the next line. So here we have 3 plus 2r plus 6r minus 1 from the r squared times the 4. Okay, now the real parts we can combine. So the 3 and the minus 4, that will be a minus 1 for the real parts. And then the 2 plus the 6, that will be r times 8. Okay, or you can write it as 8 times r. It doesn't matter which way you put it. Okay, so that's what we get for z1 times z2. Okay, you just treat it as 2 brackets. You multiply it out to get your 4 terms. Remember, r squared is minus 1. Collect your real parts together, collect your imaginary parts together, and you get your complex number back. Okay, let's have a look at division. So number 3, division. Okay, so it's a bit more involved than multiplication and addition, so we just write it as a separate section. So here, what we want is given z1 is a1 plus I b1, and z2, which is a2 plus I b2. How do we calculate z1 divided by z2? In other words, a1 plus IB1 divided by a2 plus IB2. there's not an obvious way of how we write this in terms of some real part, let's call it u, plus r times some imaginary part, let's call it v. Okay, because we've got two terms at the top, two terms at the bottom, it's a bit more difficult to work with. So what we do is a little trick. So here we've got a plus ib1 over a2 plus ib2. We multiply by 1, but this number 1 is carefully chosen. So a1 plus ib1 over a2 plus ib2. We multiply by 1, but here we're going to write our 1 as a2 minus ib2 over a2 minus ib2. Okay, so we'll see how this works now, but what we do is we take this denominator, a2 plus ib2, and wherever we see an I, we replace with minus r. Okay, so I changes to minus r. We call that complex conjugation. So we'll have a look at that towards the end of the lecture. But that's what we do here. We take the denominator, we find its complex conjugate. In other words, we replace I with minus I and multiply by that divided by that. So it just ends up being a 1. But this helps us because if we now multiply the numerators and the denominators, we will see shortly that the denominator becomes a single real number, okay, which helps us quite a bit. So we end up with a1 plus ib1, a2 minus ib2, remember the minus there, divided by a2 plus ib2, a2 minus ib2. Now let's multiply the top and the bottom. So multiplying the top, we get a1 times a2, that's a1, a2, minus I, a1, b2, plus I, b1, a2, and then we end up with a minus r squared, but remember, r squared is minus 1, so minus r squared will be plus 1. Okay, so please keep in mind that r squared is minus 1. Okay, all divided by a2 times a2, it's a2 squared, minus I, a2, b2, plus I, a2, b2, and then again we have minus r squared, b2 squared, so the r squared is the minus 1, so minus minus 1 is plus 1, so plus b2 squared. And notice that the imaginary parts cancel. We've got minus I, a2, b2, plus I, a2, b2. They go away. So there is no imaginary part to this denominator, which makes it a single real number. Okay, so we can use this technique to turn this complex denominator into a real denominator. Now, as for the numerator, we can do what we had done before. We can collect the real parts together, a1, a2, plus b1, b2, plus r times, and we can collect the imaginary parts together, a1, b2, the minus from the minus r, plus b1, a2. All of this is divided by our new denominator, a2 squared, plus b2 squared. Now we've got a single denominator because we can put brackets around that and say that's our real part, plus no imaginary part. So we can take the real part of the numerator divided by that term. We can take the imaginary part of the numerator and divide it by that term. Okay, so even though it's made up of two parts, together we call that a single term, which is the real part. Okay, so here we get a1, a2 plus b1, b2 over a2 squared plus b2 squared. All together, that's our real part, plus r times minus a1, b2 plus b1, a2 all divided by, again, this real part, a2 squared plus b2 squared. So here, again, we divide it to complex numbers. We get this as our real part plus r times our imaginary part. Okay, remember again, the imaginary part is the stuff in brackets. We don't include the I there. Okay, so everything to the right of r in brackets, that is our imaginary part. Okay, so that is the little trick that we use when it comes to dividing complex numbers. Okay, and we showed that the division of two complex numbers gives us a complex number. Okay, so let's look at two examples with some actual numbers. So let's say we have 2 plus I divided by 3 minus 2I. Okay, now we multiply the top and bottom by the conjugate of the denominator. So it will be 2 plus I, 3 plus 2I. Remember, we take the I and we replace it with minus R. So minus and a minus, that makes a plus. So we have 3 minus 2R, 3 plus 2R. That's the conjugate. Now we just multiply the top and the bottom. We know how to do multiplication. So 2 times 3, that will be 6, plus 4R, plus 3R, and then we'll have 2R squared. R squared is minus 1, so we have minus 2. All divided by, again, we can do multiplication. So 3 times 3, that will be 9. Plus 2 times 3R, let's just write that as plus 6R, minus 2R times 3, so minus 6R, and then again, R squared is minus 1, so it will be plus 4. And again, the 6R minus 6R, that cancels. So whenever you're multiplying by the conjugate, you should have that the imaginary parts cancel out. So we're left with just a real number. Okay, in the numerator, we have the real number 6 and the real number minus 2. That will give us a 4. Imaginary number 4 and 3, I, that will be plus 7R. All over 9 plus 4, that will be 13. And now we can separate this into the real part and the imaginary part. So 4 over 13, that makes up the real part. 7 over 13, that makes up the imaginary part. Okay, so that's our final answer for that division. Let's look at another example. Here we have I over 2 minus R. So in the top, we have a complex number, but there's no real part. It's purely imaginary. We could have written this as 0 plus R. So the real part is 0, the imaginary part is 1. So in general, that's a complex number, but specifically here, it is purely imaginary because there's no real part. Okay, so how do we do the division? We need to multiply the top and the bottom by the conjugate of the bottom part. So multiply by 2 plus I, because we are replacing I with minus R. So 2 minus I becomes 2 plus R. That's at the top and at the bottom. So here we have I times 2 plus R divided by 2 minus R, 2 plus R. Okay, multiplying the top, the R times the 2, that will be 2R. R times R, that's minus 1. Right, because R squared is minus 1. In the bottom, 2 times 2, that will be 4, plus 2R, minus 2R, and then R times I is minus 1, so we have minus 1, so plus 1. Again, since we're multiplying by the conjugate, we see that these imaginary parts cancel, so that and that go away. So in the top, we left with 2R minus 1. In the bottom, we left with 4 plus 1, which is 5. And now we can separate this into the real part and the imaginary part. So the real part will be minus 1 over 5 plus r times the imaginary part will be 2 over 5. Okay, and that gives us our complex number minus 1 over 5 for the real part plus r times 2 over 5 for the imaginary part. Okay, before we get to the homework, I just want to introduce some notation that we'll be using from now on. So, notation. So, given a complex number z, we can write that as a plus ib or x plus iy. So we have some real parts and some imaginary parts. Okay, and this is a complex number. So the first notation that we use is called the real part, and we write it as re of z. We read this as the real part of z, and this is equal to x. So this is the notation we use for the real part. And then similarly, we have im of z is y, and that is for the imaginary part. So if you want to refer to the real part of z, we write rez, and that gives us x, which in this case was the real part. If you want to talk about the imaginary part, it's im of z, and in this case it's equal to y, which is the imaginary part. Number 2 is that complex conjugation. So z is equal to x plus iy. We write the complex conjugate as z bar or z star. You can use either of them, that's fine. And this is equal to x minus iy. So before we had plus iy, if we replace I with minus I, we now get x minus iy. We call this the complex conjugate. And lastly, number 3, we have absolute value z is equal to the square root of x squared plus y squared. This is called the norm or the modulus. Okay. So with real numbers, we called it the absolute value. Here we can't take the absolute value of complex numbers because there are no positive or negative complex numbers because it's two-dimensional. Okay, we can't look at positive side or negative side. So instead we use this thing called the norm or the modulus. And if you look on the right-hand side here, root x squared plus y squared, that is the distance from the complex number to the origin. So here, if we have our complex plane with real parts and the imaginary part, some point here, that's a complex number z, with components having real part x, imaginary part y. Here's x, y. This distance from the origin to z, that's x squared plus y squared, taking the roots. We call this modulus of z, or the norm of z. Okay, it's that distance there, the hypotenuse of this triangle that we can form. Okay, so later on we will add some more notation and work with this a bit more. But for now, I just want to define what these mean. Okay, so let's get into the homework. Okay, and as before, homework. Okay, as before, this homework will be due on Thursday before we start with the assignment. Okay, so please make sure that the homework is written on separate paper with your name and student number on. Okay, and you will have to hand the homework in before you can start with the assignment on Thursday. Okay, so just 3 questions. Part 1, if we have Z1 is equal to 2 plus I, and Z2 is equal to minus 1 plus 3I, please find the following. 1.1, Z1 plus Z2. 1.2, Z1 minus Z2. 1.3, Z1 times Z2. Okay, I think you see where this is going. Z1 divided by Z2. Okay, so Z1 and Z2, those are fixed. Please find these four complex numbers. Okay, part 2. 2.1. Just a couple proofs. Prove that Z times Z bar is the norm of Z squared. 2.2. Prove that the real part of Z can be written as 1/2 Z plus Z bar. 2.3. Prove that the imaginary part of Z is equal to 1/2 Z minus Z bar. Okay, number 3. Determine all roots, so real or complex, determine all roots of 3.1, 2x squared plus 3x minus 1. 3.2, x squared plus 2x plus 3. And 3.3, minus x squared minus x plus 2. Okay, so just these three parts for homework. For 2.1, 2.2, and 2.3, I'll give you a hint. Let z equal x plus ry. Once you let z be x plus ry, show that you can get from one side of the equation to the other. Okay, it's quite straightforward once you use these definitions. So the definition of the real part and imaginary part, the definition of complex conjugates, and lastly the definition of the norm or modulus. Okay, so use the definitions, substitute this for z, and then that should be pretty easy to show. Okay, and again, this will be due on the Thursday before you start the assignment. Okay, so please make sure you have it ready before then. Okay, I won't be available on Tuesday, so this video, along with the following video, that will be your work to do on Tuesday. Okay, Wednesday I will be available, Thursday I'll be available, so you can come and ask any questions, or you can submit your work if you need to. And then remember, Thursday afternoon, that will be the assignment. Okay, so you will have the full tutorial period to do that. Okay, if you have any questions, please just email me or email the tutors. So the tutors have mentioned that not many students have been making use of them. Please email them or ask on the WhatsApp group. Okay, they're there to help. Please make use of them. Okay, so I will see you on Wednesday if you come to my office, or on Thursday for the assignment.